In previous videos, we saw that the drying of an initially saturated body causes inhomogeneous deformations, which may result in damaging tensile stresses. In this video, we examine mitigating strategies such as preventive conservation actions or the use of shrinkage-reducing admixtures, as well as that of fibers and/or expansive agents. In our previous video on susceptibility to drying shrinkage stress, we saw that stress arises during drying if the shrinkage is not uniform. Higher stresses occur in bodies that have a large proportion of pores with diameters below about 0.1 microns, such as mortars, when they are subject to rapid drying. This was illustrated with two kinds of limestone, Indiana limestone and Cordova cream limestone, and a typical cementitious mortar. As shown in this figure, they have very different pore size distributions. The analysis presented of the tension that can be expected when such materials dry underlined that neither limestone should suffer from drying, since their tensile strength is much larger than those drying stresses. In contrast, the mortar and other materials with fine pores may be susceptible to damage depending on the harshness of the drying conditions. In this example, the stress at the surface initially reaches 8 megapascal, much higher than the typical tensile strength of a mortar, shown here as 3 megapascal. Beyond this, mortars and other weak materials, such as adobe, are susceptible to drying stresses in their fresh state since they have a very low tensile strength. We now examine how to mitigate such problems. Prevention of rapid drying of freshly cast samples is an effective way of limiting plastic shrinkage of earthen or cementitious materials. This may comprise covering their exposed surface, protecting them from wind, or actively keeping them moist by spraying water or a curing compound. After hardening, the strength of cementitious materials is much larger, but its pores are smaller, so that higher capillary pressure is generated during drying. Unfortunately, the amount of curing needed to raise the strength more than the stress and thereby avoid damage is difficult to predict. Cracking from drying shrinkage can be minimized by using so-called shrinkage-reducing admixtures or SRAs. These are surfactants, that is, surface active agents that adsorb at the liquid-vapor interface, decrease its surface tension, and therefore the capillary pressure. With SRAs, the moisture gradient is actually steeper than without, but damage is reduced because the lower surface tension reduces the contraction and therefore the propensity to damage. The cracking risk of cementitious and earthen materials may also be addressed by adding fine fibers to inhibit crack growth. The initial drying stresses remain the same, but the material can resist these better. Overall, this mainly leads to more numerous and better distributed cracks that can be well bridged by added fibers. These more numerous cracks do not have such a dramatic impact on mechanical integrity as fewer but broader cracks. This is also beneficial in terms of durability because smaller cracks reduce the rate of water sorption. Moreover, these microcracks may become invisible to the naked eye, which, for better or worse, reduces the risk of complaints. Both of the concrete cylinders shown here were split in tension. The one on the left split cleanly in half. In contrast, the one on the right contained short polymeric fibers that bridged the crack and kept the cylinder intact. Under smaller stresses, the fibers bridge microcracks and delay macroscopic failure. Expansive agents are also found to be effective. These are compounds such as calcium oxide or calcium aluminate or sulfoaluminate cements that may be formulated so as to react after the material sets, leading to expansive forces, probably from crystallization pressure, that can at least partially offset the drying shrinkage strain. While often used, it should be noted that such solutions may enhance the risk of cracking if they do not react when intended, for example, owing to changes in temperature. A special case of materials suffering from cycles of wetting and drying is clay-bearing stones. As explained in our video, Drying Shrinkage Stress, such stones change dimensions depending on the presence of humidity, since swelling clays respond to changes in relative humidity by absorbing or releasing water from between their charged platelets. In stones that are initially expanded and then dried, this can lead to damaging tensile stresses, causing cracking perpendicular to the exposed surface. Tensile damage mainly concerns finials and decorative elements because they can easily become saturated with water. For stones that are initially dry, the wetting from their exterior surface can lead to warping and buckling, which probably contributes to the contour scaling observed on such stones parallel to their exposed surface. In both cases, the use of swelling inhibitors for clays can reduce the dimensional changes and therefore also the expected risk of damage. Compounds found to be effective in this are diaminoalkanes as 1,3-diaminopropane and 1,4-diaminobutane. They are believed to intercalate between the clay platelets connecting opposing surfaces. This prevents water ingress and thereby cancels the swelling and shrinkage that these stones suffer otherwise when humidity changes. In conclusion, depending on their strength, pore size distribution, and drying conditions, materials may be more or less susceptible to cracking from drying shrinkage. For earthen or cementitious materials, careful curing can reduce the stress level and risk of cracking. Other effective protective measures include adding shrinkage-reducing admixtures and/or fibers and/or expansive agents when preparing such materials. Finally, for clay-bearing stones, the use of swelling inhibitors can sharply reduce the swelling strain and thereby also stresses evolving during cycles of wetting and drying.